Yeah, Jake. Okay. All right. So number 4. So it says a bar 4 meters long weighs 400 newtons. So always start by making a drawing, you guys. I cannot recommend that strongly enough. Make a drawing. Okay, because the drawing will help you figure out where each of your forces lives, and it'll help you figure out what your distances are. All right, so the bar is 4 meters long. So draw a little, I don't know, whatever, one of these. 4 meters. All right, it weighs 400 newtons, and it tells you the center of gravity is 1.5 meters from one end. So that was what we were just talking about. So there's my center of gravity, center of mass. Force of gravity is negative 400 newtons, and then label your distance, 1.5 meters. Everybody good up to there? All right, now it doesn't matter, like that right there is a property of the beam. So it doesn't matter where I put my pivot point, that's where the force of gravity is for that beam. Follow? Okay. Now, it says a weight of 300 newtons is attached to the heavy end. This was sneaky. Which end is the heavy end?
The short one.
The short one? Why?
Because it's more like, it's like you're going to need, because we need to move it, like the center mass that way, it means that there's more stuff there than it is here.
Yeah, exactly. Remember, this represents the average position of mass. The fact that my center of mass is this way means there must be more mass at this end. Let me show a quick demo, and then I'll get your 2 questions today. Okay? So where's the center of mass of a regular meter stick, you guys? Right in the middle, right? Oh, so meter stick stuck, right? So there's my center of mass, right? Now where's my center of mass going to be? See, this end's heavier?
But then
It's way over here, right?
Wouldn't each side be equal in a situation like that? Where like that side technically does have more mass on it, but because of where the center of mass is located, wouldn't like both those sides have equal amount of mass?
Not necessarily, because it also, this is 200 grams,
Oh, yeah.
and the whole meter stick is only 70. Okay, so it's not just the mass that's important, but also the position of it. Okay, so this mass out here sort of counts more because it's farther out. So this weight is sort of producing more torque because it's got a longer lever arm. Does that make sense?
Yeah.
So it's not just the mass, but also the position of the mass. Right? It's like a weighted average, literally. Okay.
So for like the zero is just how many newtons the bar will take.
Correct. Or if I give you the mass of the bar, then you multiply by 9.8 and then use that. Cool. So to relate this to the lab yesterday, all of your lab drawings should have the mass of your meter stick was about 70 grams, right? So that if you multiply it out is about 0.7 or 0.6 something newtons. So you should have always had right at the 50 centimeter mark 0.7 newtons pulling it down, because that's a property of your meter stick. Make sense? You're making a scrunchy. What the hell is he talking about? It's a little cycle.
I didn't hear the first part of it. So it's at the middle of it where you put the force pulling it down, not the center of mass.
No, I was assuming the center mass was at 50 centimeters. So wherever your center mass was, whether it's 49 or 51 or 50 or whatever, that's where the force of gravity on the meter stick goes on your drawing. Good? Everybody good? I really wanted to do the lab after we'd gone over this homework assignment, but because of the circumstances, we did do the assignment. So we've been taking turns on that. Okay, so all right. So it says a weight of 300 newtons is attached to the heavy end. So, oh shoot, I wanted that to be a different color. Force, I don't know, 1 equals 300 newtons negative, right? Okay, and then bless you. And then it says a weight of 500 newtons is attached to the lighter end. So we'll call that F2, 500 newtons. Okay. I try to give my forces distinct names so I can keep track of what's what. Cool? All right, it says you place a ladder under the board to balance it. A, how much force must the ladder exert, and B, where should it be placed? All right, so does everybody understand how I got the drawing? We good? Oh, you're really quiet today. You doing okay? Yeah, no, sorry. Just second guess myself. Okay, yeah. All right, so everybody good? All right, so there's only one thing holding this up, right? It says you place a ladder under it to balance it. So somewhere we're going to put a ladder that holds it up. And question A wants to know how much force it's going to exert. Okay.
Why the 500?
Oh, it's not. Sorry. All right. So I don't know where the ladder goes, but I do know how much force it's got to exert, right? Okay, because check it out. For A, here's what I know. I know my net force has got to be 0. Why? Yeah, the ladder's not moving. It's just, sorry, the beam isn't moving. So that means that my net force, 0, has got to equal force 1 plus the force of gravity plus force 2 plus the force of the ladder. In other words, we've got 3 plus 4 plus 500 newtons down, a total of 1,200 newtons down. How much do we have to have up? 1,200 newtons. So that means that the force of my ladder must be 1,200 newtons.
Oh, that makes so less complicated.
Cool? Remember, every one of these problems has 2 equations. Net torque is 0, net force is 0. I just used net force is 0. Everybody good? All right. So now we got to figure out where it goes. So to do part B, oops. To do part B, I need to write a net torque equation. What do we have to do before we can write our net torque equation? Say it again. Sort of. So what's the equation for torque, you guys? Force times distance. From where? From your pivot point. You got to pick a pivot point. Okay? So everybody's knee-jerk reaction is to go, well, I don't know where the ladder is going to go, so I don't know where my pivot point is, right? But remember, if the bar is balanced, you can pick your pivot point wherever you want. Okay? So, let's pick a fixed location. Suggestions? Yeah, pick the end of the bar. So, draw a dot there, and label it with a P, so you remember that that's your pivot point. Why did I pick there, Addie? Because I had to pick a point somewhere, and that seemed like a good choice. It doesn't matter.
Okay.
A couple of students were in here during third hour working on this, and one of them chose this point, and one of them chose this point, and they both found the same location of the ladder. Okay? In other words, when we're done with this, the answer we're going to get is going to be 2.16 meters. Okay? The other student got 0.66 meters, but it still describes the same location. The answer here is 1.83 meters. Well, that's from this end, right? Because it's from the 500 newton meters. You see what I'm saying? So you can pick your pivot point anywhere you want. Good?
Yeah.
All right, so here we go. Only if it's rotating is the only time it would matter. If it's not balanced is the only time it would matter. So like there's one about the guy lifting the plank, that's the only one on the sheet that matters. And we'll do that one.
So we had 2.16 meters from other ends that
Yeah, because the whole board is 4 meters long. So if you do your answer minus, or 4 minus your answer, you'll get 1.83 I had. Make sense? Everybody good? Okay, so let's do this. Is it really warm in here?
No.
I think I might be pregnant.
It's like 60
Having like hot flashes. All right, so our net torque around point P has got to be 0, right? Please get in the habit of solving your problems this way. I've seen some of you just going, well, this torque equals that torque. That works for simple problems, but not for these more complicated ones. All right, so for us, our net torque is the torque from force 1 plus the torque from gravity plus the torque from force 2 plus the torque from my ladder.
Okay.
Right? Because there are 4 forces. Your lab will be the same way. You're going to have 4 forces. The 2 masses you had hanging from it, the weight of the meter stick, plus the fulcrum holding it up. So your lab net torque equation should look just like this. All right, so let's solve it. Our net torque is 0. That's equal to the torque from force 1. All right, let's see. That's negative 300 newtons times, what's the distance for force 1, you guys? With this as my pivot point, that force is 0 meters away from my pivot point, so it's 0. Plus the torque from gravity, so that's going to be negative 400 newtons times, how far is that from my pivot point? 1.5 meters. Plus the torque from force 2 is negative 500 newtons times, how far is force 2 from my chosen pivot point? 4 meters. Plus the torque from the ladder. Well, that's equal to the force of the ladder, 1,200 newtons, times D. Does that make sense? So, make sure you watch your signs. All right, so I think we're going to get this. We're going to get 0 equals 0, minus 600, minus 2,000, plus 1,200D. So you end up getting 2,600 equals 1,200D. Divide both sides, and you get D equals 2.16 repeating meters. And there's your answer. Good. But that's not the answer on the sheet. Do you guys understand why? So here's why. Look, D was the distance from this pivot point. So that means that the ladder needs to be placed 2.16 meters this way. So here's my ladder. Force of ladder, 1,200 newtons. So my answer is 2.16 meters from the 300 Newton weight. The answer on the sheet is 8.13 meters from the other end. Right? And the whole board is 4 meters long, right? See how it says 1.83 meters from this end? Oh, did I misspeak? Sorry. 1.8. So the idea is, when I describe the center of mass of this thing, or I just describe where my finger is, I can either say, well, it's 20 centimeters from this end, or 80 centimeters from this end, and it's the same thing, right? So that's all this is. Cool? So you can't just look at the number, you also got to look at the description of where that number is being measured. Cool? Questions? All right. Do you understand what I was saying? There's only one bad choice of pivot points for this. The only bad choice of pivot points is right here, because I don't know where that is. Right? When you pick your pivot point, you want to pick a point where you know where it is. Clear? Questions? Everybody happy? What's wrong? Figure it out before we move on. You must just be making a little calculator mistake or something then, Abby. I mean, did you have that same equation that I have there? The one with the red and the blue and the green? What did you choose? Oh, here's your problem. What did you choose as your pivot point? This is important, you guys. Listen up. Where did you pick a pivot point? The middle. Okay. So 2 meters? Okay, that's cool. So if you pick the middle as your pivot point, then what's going to happen is you're going to have negative 300 newtons times, when you say the middle, do you mean the literal middle, like 2 meters? Okay, great. So you're going to have the torque from this is going to be negative 300 newtons times, what's your D? Yes, except it's negative 2. Okay, so good lesson to learn, you guys. If your pivot point is in the middle, then any force to the left of it is going to have a negative lever arm.
Yeah.
Follow?
Yep.
So that's your problem, is you're missing. So this lever arm should be negative 2. This one should be negative 0.5, the 400,
Oh, yeah.
right? And this one should be positive 2.
Okay.
Good?
Yeah.
And then if you solve it, the answer you get should end up being positive 0.163 meters.
So the distance has direction.
Correct. Good? Gotcha. Everybody good? Excellent. I'm glad we stuck with it until we figured out the problem. Something easy, it usually is. All right, let's do number 7. Dennis stands atop the high dive and prepares to do a super mega colossal septuple flip with quadruple twist. He's got a mass of 125 kilograms and he stands at the very end of the board. So let's draw ourselves a diving board. Diving board. Here's Dennis. Dennis is my old roommate from Michigan State. You would like him. He's funny. All right, so here's Dennis. He's got a mass of 125 kilograms. I'm going to go ahead and just find the force of gravity on him because I'm going to need it anyway, right? So the force of Dennis is 125 times 9.8, which is a number that I don't... Is it 1225?
Yeah.
Thanks. And it's negative because it's down. All right, everybody good there? All right. Let's see. Stands at the very end of the board. The board is 5.5 meters long, and it's attached to 2 supports. So I know that this distance here is 5.5 meters. It's attached to 2 supports. The 2 supports are 1.5 meters apart, and one of them is at the opposite end of the board as Dennis. So in other words, we've got a support here, and then another support here, and they are 1.5 meters apart. Good? Now, the board has a uniform mass of 40 kilograms. So what should I do with that information? Yep, so somewhere here in the middle of my board, I got to put that 40 kilograms. So 40 times 9.8, so the force of the board is negative 392 newtons. And where is that x, you guys? 2.75, right? Half of 5.5, right? 2.75 meters, right? Because it says it's uniform? Yeah. All right, so now we got to find the force exerted by each support. So we're trying to find the force of support number 1, and we're trying to find the force of support number 2. Cool? Okay. Now, for a problem like this, when there are 2 unknown forces, you don't have to use left, right? No. There are very good choices for your pivot point, and then a whole bunch of bad ones. All right? So when you have 2 unknown forces, you want to pick your pivot point at one of those forces. So that torque is 0. Okay? So to solve this problem, I'm going to pick my pivot point to be either here or here. And it doesn't matter which one you pick. But you definitely want to pick one of those 2 points, because then the torque produced by that force will be 0. Make sense? Yeah.
Couldn't you, like, once that's happened, subtract all the rest of it?
Exactly. And then once you find one of your forces, then you just set your net force equal to 0 and find the missing one. Good? All right. Got a preference on pivot points? I usually do that too. Just pick the end. The advantage to picking the end is then you don't need to worry about negative lever arms. Follow? All right, so let's see. So I know my net torque is 0. Net torque is 0. So let's see. My net torque is the torque from support number 1 plus the torque from support number 2 plus the torque from the board plus the torque from Dennis. Oh, I can't do that. All right, are we good or no? All right, so net torque is 0, torque 1. Well, that's the force from force 1 times how far is force 1 from my chosen pivot point? times 0. Aha. So one of my forces just went away. Plus torque 2. Let's see, that's going to be force 2 times what distance? 1.5 meters, right? Positive or negative 1.5? Positive. Okay? Plus the torque from the board, that's going to be negative 392 times 2.75. That's annoying. I can't do that in my head.
Oh, come on.
Plus the torque from Dennis is going to be negative 1225 times his distance from the pivot point, which is 5.5, right? Good. And it's, I mean, so we've just got this big long equation, but there's only one unknown, and it's not a quadratic. So it's just algebra through it, right? So you're going to get 0 equals 0 plus 1.5 F2 minus 392 times 2.75 is 1,078 minus 6737.5. And I'm going to trust that you guys can solve it from there, right? So F2 ends up being, let's see, plus 1078 divided by 1.5, and you get 5,210.3 repeating newtons. All right, now, it's positive. What's that telling me? That it's an upward force. Okay, so is everybody good up to there? Have I lost anybody? Everybody's good? All right, so how do I find the other force now, you guys? Yeah, set up a net force equation, not a net torque equation, a net force equation. Okay? If you really want, you can repeat this process, but pick this as your pivot point, but that's a pain in the ass. The easier way to do it is to just say, oh, I know my net force is 0. All right, so let's do that. I just need... Where's the thing?
Okay.
Oh, here it is. Oh, there we go. Okay, so let's see. Net force is 0. So net force is force 1 plus force 2 plus the force of the board plus the force of Dennis. Let's plug in our numbers. Our net force has got to be 0. Force 1 is what we don't know. Force 2 is 5,210. Force of the board is negative 392. Force of the Dennis is negative 1225. You get 0 equals F1 plus
Wait, why did you do that force?
what do you mean?
Oh, never mind.
Was that a genuine never mind or a... So you get that. So when we solve this, what are we going to get for F1, you guys? Negative 3593.3. Why is it negative?
Because it's like pulling.
Yeah, it's a downward force, right? All right, and some of us were talking about this before the bell rang, but I want to make sure you guys understand this. Think about it. What's the purpose of the two supports? When he jumps, force 2 is holding the board up, right? But now think about this pivot point. What is Dennis doing to the other end of the board by standing there? He's pulling it up, right? Because it's going to torque this way, right? Right? Wouldn't it like tip over like a teeter-totter? And so this thing is holding that end of the teeter-totter down. Cool? And notice the math told me that. So I keep saying to you guys, trust the math to tell you the signs. That's what I'm talking about. Good or no? Trust the math, that's right. Okay. Are we good, you guys, or no? All right. All right. I want to talk about the lifting the door up problem. That's going to come up in the notes that we're going to do on Monday. So I think I'm going to hold off on that if you guys are okay with that. Sorry? No, we can talk about the lab. So, are there questions on what we did here today? Yeah, run it. Oh, no, you're just... Gotcha. All right, so the lab. So did everybody yesterday at least collect the data to figure out where the weights had to be placed to balance on the front of the page and where the fulcrum had to be placed to balance on the back of the page? All right, so let's do this. The only thing I want you to do this weekend is see if you can do the calculations for trial 1 on the front and trial 3 on the back. All right, and then we'll talk next week. Is that reasonable? All right. So my question then is, I'm wishing I'd given you guys more guidance on the front end of the lab, and I apologize for not having done so. What? Oh, I guess, yeah, I don't need to be recorded. Thank you.